So an example of this application is building mosaics. So let's say we have two images of the same scene from the same position but different camera angles. As we've seen, the mapping between the two image planes is a homography. So we can find a set of corresponding points between left and right images, either manually or automatically. So the homography matrix is 3 by 3, which has 9 parameters. However, it's only determined up to a scale factor, so there are really only 8 degrees of freedom. So we need at least 4 corresponding point pairs. Each point pair yields 2 equations, one for x and one for y. We can use more, of course, and solve using least squares. We then apply the homography transform to one image to map it into the plane of the other image. This is an example of stitching together lots of images of this scene from different viewing directions into a single composite scene, as if the camera had been a very wide angle lens. Here's another example application very similar to this, which is generating an orthophoto. An orthophoto is an aerial photograph geometrically corrected such that the scale is uniform. Essentially, it's used to turn a photograph into a map that can be measured, that can be used to measure distances. So essentially, we have an image taken from a camera that is viewing the ground at an angle. We would like an image as if the camera had been pointing straight down. So one way to calculate the transform between those two images is to find some known control points in the input image and specify where those points should appear in the output image. So what's often done is to place some control points that have been surveyed on the ground, for example, a large white disk. Those points are visible in the image. We also know they're true 3D coordinates, and then we can specify where those should appear in the output. So here's an example of doing that. Here is an image of a wall taken at an angle. Let's say we want to transform that image as if it were taken perpendicular to the wall. So we find some control points in this image. I'm going to use the intersections of these bricks. So there are 4 bricks, 4 corners of brick intersections that define a rectangle like this. And I've measured the pixel location in the image, the XY coordinates of those 4 points. Then I went out and I measured the actual physical dimensions of the bricks. They're about, each brick is about 23 centimeters high. So with that information, I know that the size of my rectangle is 184 centimeters high and 299 centimeters wide. So I'll assign the locations of those control points in the output image at a scale of 1 centimeter per pixel. I'll put the upper left point at 0, 0. This guy is going to be at 299, 0. This is going to be 0, 184, and 184, 299. So we've seen how to calculate transforms and map output images. Matlab, of course, has functions to do that for you. There's a function called CP to Tform, which stands for control points to transform. So given 2 sets of control points, it will compute the transform for you. There's another function called IMTransform, which transforms one image to another using a predefined transform. So this is the code that transforms that image of the wall. So here is the input points of image 1 in terms of pixels. Here's the desired output points in terms of centimeters. This function computes the transform using CP to Tform, and this function transforms image 1 to the output image. So let me go ahead and run this. grab this code again. Okay, so what it just did was read in the input image, mark the control points with these red squares, calculate the transform, and map the output image to this image here. So if I were to look at, for example, the transform T-form 1, let's see, where's that? So T-form 1 is a structure that contains a bunch of information. The actual data is in this thing called T-data. So to see what that is, I'll type tform1.tdata, and that's also a structure containing the transform matrix T and its inverse T inverse. So tform1.tdata.t is the 3x3 matrix that was used to transform that image. One thing we see in this result is that the output image has that area in the form of a rectangle, where those 4 points I defined here. However, this upper left point is not at 0, 0. So the reason it's not is that IM transform automatically enlarges the output image to contain the entire transformed image. So to see the location of the output image in the output space, we can actually have it return X data and Y data, which are the limits of the output image. So let me go ahead and grab that. So X data is a vector ranging from -45 to +413. Y data goes from -84 to 279. So taking my output image here, we go ahead and look at the locations. I believe the upper left corner was about here, which is sitting at x equal 50, y equals 86. So that's the offset from the upper left corner where it should have been. Okay, let's take another image of that same scene. We'll do the same process of finding a transform to map this image also to an orthophoto. But let's merge it with the original scene. So to do that, I have to map this output image into the same space as the other output image. So I'm going to explicitly set the output coordinates for those two images. So in Matlab, this IM transform allows you to specify the x and y coordinates of the output image. So I'm going to say that the output data should range from -50 to +550, and the y should go from -25 to +250. So I picked these kind of arbitrarily. I could pick larger values, in which case I would just have an image with more black. I apply the same transform, well, the other transform, but the same output coordinates for the other image. And then I'll combine the two images. Both of these now are in the same output space. I'm going to take half of the image from image 1 and the other half of the image from image 2 and merge that into a combined image. So this is the output 1 image. You can see there's some black here. This is output 2 image. I'm going to take the left half of this image and the right half of this image and just stick those together. And this is what I get.